Hello and welcome back. So let's take a look at our list of turbulence models. So we're working in the K-Omega family. So these three guys are gone. Now we're going to address the K-Omega SST-SAS Scalable Adaptive Simulation. So this is still K-Omega family of models. It's a low rate, high rate, but with better resolution. Also, it can classify as a scale adaptive, scale resolved simulation. So let's visit this turbulence model, and hopefully this won't be a long video. Okay, so let's take a look at the K-Omega SST-SAS in OpenFOAM. So here we are in the source code. So as you go here, open the source code, you're going to get a reference, now the implementation of this model. If you want, also you can take a look at the source code, some comments. So here you start to see that this model now resolves the scales. You have this delta now used for the scale resolving simulations and so on. But well, let's focus in the reference now to get some theory. So in this case, I don't have slides about this one. About this method, I have been a little bit lazy, so writing these equations and getting everything. No, I haven't had time. But in any case, let's use this the implementation paper. So the main references is ANSYS, this presentation. So these are the authors. So mentor, the same mentor from the K-Omega SST and so on. And here you have some references about some explanation, brief explanation about this method and some figures on what is happening. So as I mentioned, this method it still is a RANS method in a steady, but then when you go to unsteady, it will tend to resolve the spectrum. It will incorporate von Karman length scales into your solution. Okay, so instead of using the grid as a filter, it will use those length scales, and then it will do the computation. They have the new equations and the new coefficients that needs to be calibrated and functions and so on. But here you look at nice results. Now the comparison, now you have some experiment here and comparing the SAS here against the standard SST. You see that it doesn't capture dissipation here. Now later, if you are not familiar with this, later we're talking about what is happening here, but look at that, the SST SAS, it works well with the diameter. Okay, the K epsilon doesn't give good results, and then the comparison with the less. Okay, you have it there. So I prefer to use this paper as a reference. So I have it here. So here I highlight now the interesting stuff. So first, okay, this method, as I mentioned, adjusts the turbulence less scales. Then also, as a measure of local flow length, okay, it will introduce the von Karman length scale, as we mentioned from the other presentation. But here some other interesting comments that the resultant model, it is a RANS. Now it will have that proper behavior RANS solution for stationary flow. So you can already get an idea that here we are going to obtain correct results. Okay, this is a RANS, the flat plate, but then also on the other hand, for flows with transient instabilities like those in massive separation, the model will solve those, will use the length scales and solve those scales similar to what you can get with less. Okay, so that is the advantage of this model. So here you have some figure images, some comments of the equations. So look at that, the difference here is you look at the equation will be the SST, but then you introduce this new term, and here you have your von Karman scales that are going to work as a filter. Now instead of using the mesh, you use those scales, and well, then you will have a lot of development here about how things are computing and so on. But it's a very promising model, and actually this model, it appeared after the DES models, okay, and before some other more advanced models. So it's something in between, but it classifies as a SRC models, and very interesting results. Okay, so you have here some other interesting reference. This is a good reference for that model. So the initial development by mentor, you have it in this one, in this reference. So now let's move to this case. So let's go here, and we have K-Omega SAS. So again, we have a solution. Okay, I'm not going to run the case. It's pretty much boundary conditions set up exactly the same as the SST. Okay, so how you set the values here. So probably let me erase the epsilon, we don't need it there, and okay, so I leave it there. I don't know why you need that quantity. So everything is exactly the same if you open, and just to confirm there, just to show you. Okay, so basically as we chose in the values in the previous case, also here for omega. So remember, close to the walls, this K-Omega SST will be a RANS. So the theory is exactly the same. Okay, and then important that, let me go in constant when you choose the model. Okay, so here model transport, so you choose the model, but then you need to give this delta. Now this is a quantity to filter and so on, so you need to give this quantity. This is just for scale resolving stuff, but you need to define that, and that's all. For the rest is you go also to numerics, nothing changed. Okay, so this, as is based in the K-Omega SST, you need to define all the patch wall distance, but there you go. So let's take a look also here at PowerView. I'm not going to open up PowerView, already have the solution. So first we're looking at the HRE. So this is your HRE, and look at that, we have a very good agreement there, as we are expecting, because we know that it will default to a RANS now in these conditions, steady condition. So we have this plot here, and then we go traditional plot, and see that actually it's appeared that this method defaults to the standard K-Omega SST in their steady condition, because we get exactly the same behavior as we were getting with the pure K-Omega SST. Then also let's take a look at here, we have the low resolution. Okay, and let me open this, and perfect behavior, nothing strange as we were expecting there, production, dissipation, and so on. And here also the match, a very good match with our correlations and so on. So there you go, and just to open here and compare with the K-Omega SST, the HRE, where we have that funny behavior, and it shouldn't be this one, it should be this case, and there you go. So if we compare both of them, this will be okay. Oops, I'm getting now here a little bit lost in translation. Okay, there you go. So pretty much they think, actually I think they are exactly the same solution, probably small differences here and there, and actually yeah, I think I see something here, but pretty much the same stuff. So as you see, we went to another model of the family K-Omega SST. Okay, the SAS model, exactly same setup, and let me add that it makes absolutely no sense to use this model if you are doing steady simulations. That in this case is you are going to on a steady with separations. You can test this one, will be now close to the other, to the des models and less models and so on. So yeah, with this being said, we covered this model, and we have covered a lot. As you see, there is a lot here to study. So let me go here and cross this model. So now another one bites the dust. Okay, it's gone, and at this point we have covered the most important K-Omega family of models. So we're going to revisit this one. Okay, and probably so it's better to use some cases that where we have the unsteadiness, but remember that it will default under these conditions that we have this flat plate, will default to the K-Omega SST. Will be more interesting when you have separation and so on. So then we are going to keep working with the K-Omega SST. We have another punk here in that family, so this is the transition one, so probably it will be better to work with a transitional case. So at this point, I think that the next videos we're going to focus is parallel matters, and then we move to the K-Epsilon family of models that we have many of them and many interesting things to discuss. These two also enters into the same category of K-Epsilons. This will be transitional models that we're going to let it to the end. So also in between, we're going to talk a little bit the coefficients that you have seen in turbulence models, something I will introduce something as well about the near wall treatment, and we talk about Y plus, Y star. So I'm going to show you that later when we start to cover the K-epsilon. And yeah, that's it. So at this point, I think I'm done with this video, and I hope to see you in the upcoming ones. So thank you for your attention. See you next time. Bye.